We start? Okay, so hello everybody. My name is Despina Hadjifotiadou, and I'm here together with my colleague Stefano Panebianco in the control room of the ALICE experiment, and they will take you for a tour of the experiment. So first, let me do a very brief introduction about where we are and what ALICE is. So we can now see the film, see the PowerPoint. Okay. So what you see here is an aerial photograph of CERN with the circles. You see the accelerator. The big circle is the Large Hadron Collider, the biggest CERN accelerator. And you see the 4 experiments where the 2 opposite circulating beams collide, and the experiment register what comes out of the collisions. ALICE is one of the 4 experiments situated at the point 2 of LHC. There are 8 points all around where there are shafts going down, and because the LHC is installed 100 meters below ground. And here you can see an aerial photograph of the installations on the surface. ALICE is installed in ALICE is in the border, on the border between Saint-Genis-Pouilly and Cergy, 2 French little towns very near CERN, which is on the border between Geneva and France. So this is a photograph of ALICE. You will see it later during the tour. The name of ALICE stands for a Large Ion Collider Experiment, since ALICE is the experiment of LHC which is dedicated to the study of collisions of heavy ions, and more specifically lead nuclei. All the apparatus of ALICE is 16 meters high, 16 meters wide, and 26 meters in length, and it weighs 10,000 tons. Most of the weight is this red structure, which is a big magnet. You will see it during the tour. And all this is installed 56 meters below ground. Here you see ALICE schematically. You have what we call the central part, which is inside this big octagonal red magnet, and a separate part, which is the spectrometer for the muons. And the collisions of the 2 beams happen in the middle of this central part. And you see this here schematically. Now, why heavy ion collisions? If we go back to the Big Bang, which is the most accepted theory about how our universe was created, at the moment of the Big Bang, which happened 13.8 billion years ago, all matter in the universe was created, and in the very beginning, meaning microseconds after the Big Bang, under conditions of extreme temperature and extreme density, all matter was in the form of free quarks and gluons. In parentheses, quarks and gluons are the constituents of protons and neutrons, but in normal situations they cannot exist free. But for a very brief time after the Big Bang, they were free, they were deconfined in a state that is called quark-gluon plasma, which of course lived a very short time since the universe was expanding, which means the temperature was falling, the density was also falling. So after a moment, the quarks and gluons were combined and were confined permanently inside the particles, which we call hadrons. In nature, we have protons and neutrons. So in ALICE, what we do is that we try to recreate tiny droplets of this primordial matter, and this we do by colliding lead nuclei. So here, if you can play you see the animation. We collide the lead nuclei, which travel almost with the speed of light. That's why they appeared like disks, because of relativity. And the result of the collision is that their constituents, we can say, they melt due to the very high temperature at the point of collision, and also the very high density. So for a very short time, we have a tiny droplet of this quark gluon plasma, which lives a very short time. In the experiment, its lifetime is of the order of 10 to the minus 23 seconds, because it goes through a number of transitions, and eventually it becomes hadrons, meaning particles in which the quarks are confined. And this is what we see with our detectors. But still, doing these collisions and observing the result of the collisions after hadronization, we can get information about the behavior of this state of matter, and also understand how the transition happens. So in this sense, we get information about our universe in its very beginning. So all this is done by the ALICE collaboration, which is a collaboration of more than 1,900 people from 175 institutes from 39 countries that you see in this map. So now for the tour. Unfortunately, we cannot do the tour live, because as Stefano will tell you later, this is exactly a period when there are tests with beam in the LHC. They're trying to send the beam from the previous accelerator to the LHC ring, and ALICE is near the injection point, where the transfer line meets the LHC ring. So we do not have access in the cavern. Therefore, we'll show you a pre-recorded tour so that you can get an idea of the various components and of the whole installation. So we can now see the film, the video of the tour.
Welcome to point 2 of LHC, the Large Hadron Collider. We will visit together ALICE, which is one of the 4 big LHC experiments. ALICE, its name stands for a Large Ion Collider Experiment. It is designed to study collisions of lead nuclei, which travel almost with the speed of light. And the interest of these collisions is that they recreate tiny droplets of the quark gluon plasma, which is assumed to be the primordial matter. So let's go inside to see the experiment. Here we are in this big hall. Everything that you will see downstairs inside the ALICE cavern has come through this hall and gone down from the shaft using the big crane that you see there, the yellow structure. Here you see the ALICE Run Control Center, where people have started working, commissioning the detector, ready to take data when LHC starts in a year's time. All the controls are done from the surface when LHC is running, since nobody is allowed downstairs. To go down, the person access system of LHC checks my personal dosimeter, and then I have to go through the biometric control so that the system verifies, looking at the iris, that the correct person enters. You can see here on this map showing the whole accelerator complex of CERN. ALICE is at point 2 of LHC, near the point where one of the beams enters LHC from the previous accelerator, the SPS. We will now go down 51.2 meters below ground to the less deep point of the Large Hadron Collider. So here we are in front of the main part of ALICE. ALICE is actually made of two parts. This central part, which is inside this big magnet, and the separate part that we will visit afterwards. This red octagonal structure is a big solenoidal magnet. This magnet is a conventional magnet, meaning that it works with cooled with water at room temperature. There is a coil where inside, where a current of 30,000 ampere creates a magnetic field of half a Tesla, which is parallel to the axis of all this structure. These huge doors that we see close when the experiment is running, when the magnet is on, and the operation of closing them or opening them when it's necessary is a slow one. It lasts some hours, since each door weighs 350 tons. The whole of ALICE weighs 10,000 tons. A big part of the weight is the magnet. And the dimensions are 16 meters the height, 16 meters the width, and 26 meters the length. Inside the magnet, along the axis, there is the beam pipe, a tube where there is high vacuum, and in which two beams come from the two directions and collide in the middle. And around the beam pipe, there are detectors in cylindrical geometry, many layers, one around the other, which see in quotation marks the particles produced from the collisions. So you can imagine that all this huge construction is a very big digital camera with some billions of pixels, which takes photographs of the collisions. We are near the heart of ALICE. Here there is a compensator magnet. It compensates for the magnetic field of the dipole on the other side, on the side of the muon spectrometer. And the beam pipe goes through it and enters into ALICE. The collisions take place at a distance of the order of 3 meters from the black disc that you see, which closes the detectors behind it. The beam pipe is under very high vacuum. This is necessary because otherwise the beams would collide with the air and would get destroyed. In most of the LHC, there are two beam pipes for the two beams circulating in opposite directions. But of course, through ALICE and similarly through the other experiments, there is only one beam pipe so that the beams can meet in the center. So if you could see behind this red disc, you would see components of a detector called FIT, Fast Interaction Trigger, that was installed recently. And behind it, you would be able to see the inner tracking system, the inner silicon detector, which is made of 7 layers of more than 12 billion pixels. The signals already at this level are transformed into optical signals and go up to the computers for recording with optical fibers, and then they are transformed again into digital information. So this is the other part of ALICE, the muon spectrometer. Here the magnetic field is 0.6 Tesla. And for the detection of muons, we have 10 stations consisting of gaseous detectors. You see 4 of these stations, these huge panels which support the detectors. There are another 6 stations inside the magnets. In addition, there is an absorber inside the solenoid. You see it here, it's this cone. This is again there to absorb other types of particles and let through the muons. And finally, after the last muon station, there is an iron wall. This is 1 meter thick and serves as a filter. It cuts everything else that is not muon. Up to now, LHC was providing 600 million collisions per second. So it is not possible, nor is it interesting to record all these collisions. Therefore, all experiments have the trigger, a system that uses the information coming from the hardware in order to decide if the collision was interesting and so record it, or if it was not interested, it gets rejected. And here you can have a view of the muon spectrometer from the top. You can see the iron, the blue structure, which is what closes the magnetic field, and the 2 poles of the dipole magnet. So this was the end of the visit. We'll now go up on the surface. I hope that some of you can visit ALICE in reality during the next shutdown.
Tell you what's happening right now in here.
I hope so. So I will try to make a short visit of the ALICE control room. So as Despina just said, we were not allowed to go down to the cavern because of present tests that I will go to explain in a few moments. So I will try to show you with my camera if I can. Hopefully it will work. Okay, yes, I guess. So you see from here the ALICE control room. So we are in the weekend, so not so many people. If you have come yesterday, it was very much crowded. So as was said, the control of the experiment happens from the surface. So here we are really on surface at the ground level, while the experiment is 60 meters on the ground. So you can see here a lot of, let's say, positions and screens and so on. Because as Despina just showed, the ALICE experiment, as every high energy experiment, is made of large list of different detectors, sub-detectors made of different technologies. And this has to be centrally integrated and monitored and managed by experienced people. So we have here a way of functioning which is made by shifts. So we have a crew of people who takes care of the different aspects of the experiment. There can be cooling, high voltage, low voltages, the readout, the data acquisition, and so on. And we also monitor the state of the accelerator system and of all the ancillary systems of the experiment. So the reason why you see you could not see the underground cavern today is that we are in a phase where all the different accelerators of the CERN complex are restarting. And indeed, yesterday was the first time we received some particles in the ALICE cavern. And this was very exciting because indeed what happened is that at the moment the LHC is trying to insert some beam into the LHC, not really up to the LHC, just up to the transfer line. So as you probably already know, the proton beams coming from the superproton synchrotron are then inserted inside the LHC via transfer line, which is very close to the ALICE experiment. Indeed, this transfer line is to be tested. So what happened yesterday is that we received protons in this transfer line, and they were shot on the beam dump, which is called the TED, transfer line external beam dump, and the interaction between these protons coming from the SPS with this beam dump creates a lot of particles, in particular pions and kaons, which then decay into muons. And the result of this is that we received in the cavern and our detectors a bunch of muons, which let's say, are interesting particle for us because they are very good for testing and for qualifying the detector. So the detector was fully on yesterday, so we could take data until late in the night. And this was very interesting, very successful, because this is the first time that our upgraded experiment was able to really take data, let's say, apart from cosmic data and no. So this was very good. And in the coming month, our commissioning will continue. So as the spin already said, we are now with an experiment which is fully refurbished, very much upgraded with very more modern technologies. And so this new experiment, in a sense, needs to be fully recommissioned. So this is what we are doing since already many months. And in the coming weeks, what's going to happen is that we will receive the first beam, the LHC, which we call a pilot beam, which will be not accelerated up to the nominal energy, but this will enter inside the LHC beams. This will be circulated through the beam pipes, and then collisions will be provided in the center of the ARIES experiment as for all the other experiments. So this will be the first occasion for us to study the first proton-proton collisions in our upgraded detector. I think that's more or less all for the this short overview of the room. Maybe we can go through the Q&A session.
Well, there are no questions at the moment, so
Let's give the time people to
no. No, there are not. I don't see many questions. So maybe if we can have the presentation again, we can say some things about the upgrades that happened during the shutdown of LHC. This, especially these last 2 years, and
in terms of I think that is the problem that not really what the plots are not updated.
okay, we have this. Let me see. No, I have lost the connection. Can you go to the? Can you go back to the slides? Okay, you can stay here. No, can you go to the previous one? No, go back. One more back. There is one missing, I guess. Okay, go then forward. Okay, one more so that we can see the detector. Okay, so you see here the schematically the ALICE detector, and what we did during the last 2 years when LHC was stopped, and it's still stopped, is a major upgrade of the experiment. The reason is that LHC will go eventually during a major upgrade so that it will have higher luminosity. This will be during the next stop. But already during this shutdown, the injectors went through various improvements. The purpose of all this is to have a higher luminosity, which means higher number of collisions per unit surface and per unit time, which results in a higher number of collisions per day, per week, per year. And this is important because we're interested in very high statistics, since the phenomena we are studying are, they're a question of probabilities, and in general, we're looking for rare phenomena. So we need many millions of trillions of events to observe rare phenomena and maybe find new particles if they exist. To be able to deal with higher luminosities, which means higher rate of collisions, we had to upgrade our detector, especially since the central one was relatively slow. This had to do with how this detector works. Since this detector is designed to be able to detect and tell apart the many thousands of charged particles produced from one very central lead-lead collision. In LHC, there are collisions of protons and lead nuclei for the heavy ion run. And in the case of lead nuclei, since the lead nucleus is much bigger than the proton, it has 82 protons and 126 neutrons. If in the collision the whole nucleus participates, then we can have many thousands of particles produced. So we need a detector that can detect all these particles. And this is a detector called time projection chamber. But since this was relatively slow, in order to be able to be faster to deal with higher collision rate, we have upgraded it, meaning that we have replaced the chambers that are reading the signal created in this detector with other chambers so that it can work much faster. Also, we changed our very central system. You saw during the the virtual visit, it was mentioned that we have 7 layers of silicon pixels, which make up a total of 12.5 billion pixels. This is a new system. It replaced the previous one, which was made again of silicon but using different technologies. The new system will provide much higher precision in finding the passage of the particles through the pixels. And also, since we go nearer the interaction point, because we also changed the beam pipe, so we have one of a smaller diameter, we will be able to find the particles which are short-lived, and this because these short-lived particles, we don't see the particles themselves, but we see their products, and we can, by reconstructing their trajectories, we can find where they were produced. This is what we call a secondary vertex. So this new silicon tracker will provide higher precision in finding this secondary vertex. We also did other changes. For instance, we installed silicon detectors in the system for the detection of the muons that Stefano is responsible for. And this also will provide higher precision in finding the point of origin of the muons. We also changed our the whole way in which the data are read out, so that we can take much higher rate than before. And because of all these changes, now what we are doing since some months, and we will continue for some more months, so that we are ready when beam comes next year, we do the commissioning, meaning testing each detector separately and then integrating it in the central system. And then we will also take cosmics. We will use the muons from cosmic rays in order to test the performance of the detector, the alignment, and so on. So let's see if there are any questions. I don't see any question. I don't know if Stefano would like to say something else. Let's see. You see that in the control room, since we are many people here, we are obliged to wear masks. Stefano, do you want to say something else?
I don't know whether there are questions. I guess uh, you can maybe answer. No,
I,
from the operational point of view, maybe, yeah. I don't know what else to say.
I don't see any questions in the Google Doc.
Perfect then.
Maybe we can say some things about what we see from these heavy ion collisions, namely what we have learned from the study of the quark gluon plasma. Do you agree?
Yeah, sure. Please go ahead.
Okay, so in ALICE, we do not discover new particles. At least this is not the main purpose of ALICE. As we mentioned, we want to study the properties of this primordial matter, which we reproduce with the heavy ion collisions. And we have found up to now many interesting things. One of them is that the temperature of the initial state, let's say at the moment that it is created, is some trillions of degrees. This is really a very high temperature. This is many 200,000 times higher than the temperature in the core of the sun. But of course, this is a temperature at the point of collision in nuclear dimensions. I mention this because sometimes people ask, and this is normal, what happens? Don't things melt from this high temperature or something? This is a temperature really very localized. And anyway, the collision takes place in vacuum. Uh, and in reality, this is the equivalent, let's say, of the energy, because all the kinetic energy of the colliding particles is transformed into mass, which means that the particles that we see, the new particles that we see in our detectors. Anyway, this is one of the interesting things, and actually, this was put in the Guinness records by some other heavy ion experiments in the States. This is in parentheses. In the States at Brookhaven, there is a dedicated heavy ion collider called RIC, Relativistic Heavy Ion Collider. There they collide beams of gold, which is also a very heavy element. And these experiments before LHC, they had measured this high temperature, and they had put it in the Guinness record as the highest man-made temperature. By the way, one of the ways of measuring this is by seeing the photons emitted by this state as it cools down. Another thing is that, again, this was observed first by the experiments at Brookhaven, but the experiments at LHC, when we had the first lead collisions, confirmed it, is that this state of matter behaves as a perfect liquid. This came as a surprise when it was first observed, because since plasma, normally with plasma we associate a behavior of gaseous behavior with unrelated movement or uncorrelated movement of the constituents. Here we see that they flow with a very low, almost with no friction, and therefore we say that this behaves like a perfect liquid. Other things that we see is that we have absorption of energy in some cases, and this must be due to the interactions inside the plasma for a, let's say, for a very brief moment when this quark gluon plasma, this very hot and dense state, and the particles that start being produced and go out, when they coexist, we have interactions inside the plasma which do not, let's say, so that we miss some energy, we don't measure it. So this is one another thing that we have observed. What else could we say,
Maybe this
Stefano?
is something that I can add. Yes, something that was really unexpected and that shows that we did not understand everything on this subject. And we still have a lot of open questions to solve. Is that what we expected historically was to produce this very particular state of matter only in heavy ion collisions, meaning that our idea was that we need big nuclei with a lot of neutrons and protons which interact at high energy in order to create the thermodynamic conditions of the formation of this state. What we discovered just a few years ago, just at the end of the run 2, was that indeed, in very specific condition in a proton-proton collision, which for us are not supposed to be, let's say, enough to create this state, in very specific condition, in particular in events where a lot of particles are produced, we call the high multiplicity events. In some particular case, we see what we call collective effects, meaning that it seems that the constituents of the proton which interact with themselves uh, exhibit a collective behavior which is quite similar to what quark gluon plasma is. And this opens a very big field of questions and studies because this means probably that even at a low energy, it is, or a lower temperature, is already quite possible to deconfine quarks and gluons from hadrons and have enough temperature in order to have a state transition from what we call the hadronic state, which is the normal state of matter of protons, neutrons, and all the particles, to a more deconfined state where the quarks and gluons, which compose the hadrons, are in a sense quite deconfined. So this was a surprise, and a large part of the program that we are going to start next year, as soon as the HC restarts colliding proton beams, will be exactly this. Will be to go well beyond our present understanding, accumulate much more statistics in, or not only in lead-lead collisions, but also in proton-proton collisions, in order to really study in detail this kind of.
Just to say that in I don't know if Stefano mentioned it. In all these years, on 2 or 3 occasions, we also had collisions of one proton beam with one lead beam, meaning asymmetric collisions, and this was done in order to decouple uh, the role of nuclear matter in this, because if we assume that in this case we don't have the creation of a quark gluon plasma, still one proton interacts inside a more complex system inside the nucleus. So this already produces some effects, and we wanted to decouple that. And there also we saw behavior that might lead to the conclusion that maybe even in this case we have the creation of quark gluon plasma, depending on how many results we have in the final state. Uh, Let me see. I don't see any questions. Let me see. Do I have? No. No. Okay. Yes. Okay. Okay. So, Stefano, how do you say? Shall we end it or?
Yeah, I think it's we said everything we could.
Okay. It's a pity that we couldn't really gone downstairs, but okay, this is the program of the accelerators and the experiments has priority over visits, so we couldn't
Yeah,
change it. Okay, so I think we can thank whoever watched,
yeah.
and
Thank you very much.
we hope
Even though we
that.
don't know, we hope
But
that we.
is it registered so accessible on the YouTube later on? I see this question. Yes, I think the idea is that it will be registered so that people can watch it. This was my understanding, at least. Okay.
Perfect.
Okay. Let's hope that at some point it will be possible to have people coming back to CERN and visit in person. And of course, visits underground are possible only when there is no beam. But okay, hopefully there will be such occasions, at least for some of the audience. So I think we can say goodbye since there are no questions. And
Goodbye.
thanks a lot for the attention. Bye bye.
Bye bye.